So question 2, we're looking at this reaction, and the first thing it asks us to do is to write down an expression for Kc. So double check, it wants Kc, not Kp. If you go off on the wrong track there, you're going to get into all sorts of trouble. So yes, it definitely wants Kc. And the second thing to check is whether it's a homogeneous equilibrium or a heterogeneous one. Remember, if it's heterogeneous and you have a pure solid or a pure liquid, you're going to leave it out of the equilibrium constant. Or if you have a reaction in aqueous solution and water is also not just a solvent but a reactant, then again you're going to leave it out. So you've got to check that one carefully because it has got water involved, but it's steam, it's water as a gas, so it's not a solvent, which means you don't leave it out. And therefore the expression is just given straightforwardly by the usual recipe. Kc is equal to the stuff on the right goes on the top. So the concentration of H2S, must use the square brackets to mean concentration, times the concentration of H2O squared, because there are two of them. So that's your top line. And then the stuff on the left goes on the bottom line. So divided by the concentration of SO2 times concentration of hydrogen cubed, because there are three of them. So that is your Kc expression. The next part is asking us to find the value of Kc from some experimental data. Now when you get these questions where it says this is the mixture you make to start with and then you let it come to equilibrium and here's one of the concentrations at equilibrium, as soon as you see that it's a question like that, you really should think about setting up a table. And it's a table which has the equation written across the top, not just headings with the substances, but the equation with these right balancing numbers there, because they're going to be crucial in your working. And then down the side it's going to have the initial moles, meaning what you put into the pot to start with, the equilibrium moles, meaning what's in the pot once you've allowed it to come to equilibrium. And then depending on whether it's Kp or Kc, you're either going to go into mole fractions and partial pressures, but in our case, because it's Kc, it's equilibrium concentration. Now if you know that this is the way to do these questions, you can save a huge amount of time by just going straight in and setting this up, rather than trying to invent your own way of doing it. Because you may get there in the end, but it's going to take you longer, and because this is such a compact and efficient way of doing it, you're much less likely to make mistakes. So what the question tells us is that to start with, we have 2.5 moles each of these two substances, so we can write those two in. It doesn't mention having any of these, and if it doesn't mention them, that means that there wasn't any, so these are 0 to start with. And it also tells us that once it reaches equilibrium, we now have 0.350 moles of H2S. So we can write that one in as well. So those data all come from the question, and that's all that the question tells us. So the rest of those numbers are going to have to come from calculation. So what you do is you look at that change and you say, right, how much did that change by? And you can see it went up by 0.35 moles. Now remember that what the equation does is relate the relative number of moles of each substance that are either made or used up in the reaction. So if 0.35 moles of H2S have been formed, this 2 here tells us that twice as much H2O will have been formed. So that will have gone up as well, not just by 0.35, but by 0.35 times 2, which takes us from 0 to 0.700 moles. Okay, and that's why having the equation across the top is so useful, because it just makes it really easy to see, oh yeah, that's going to go up by twice as much, so we just put the number in. Now the substances on the left, if we've been getting more of the stuff on the right, it must mean that we've been using up the stuff on the left, so these ones are going to go down, and again the equation tells us how much they're going to go down. Because if one H2S is formed, one SO2 is used up, because we've got 1 going to 1. So this is going to go down by the same amount that this went up, which is minus 0.35. And if we take 0.35 away from there, that gives us 2.15 moles of SO2. Now the hydrogen we've got to take account of the 3. Okay, so that's going to go down as well, but it's going to go down by 3 times as much. So that's going to go down by 0.35 times 3, which is 1.05 moles, and so that's going to go to 1.45 moles. Okay, so that's all very efficient and easy if you use this recipe. You have to remember then that you can't just put the moles straight into the Kc expression. You've got to turn them into concentrations. The only time you can get away with putting moles in directly is when you have equal moles on either side of the overall equation, because then putting the extra volume corrections in, they're going to cancel out. But that's not the case here, because we've got 4 moles on the left, 3 on the right, so those are not going to cancel. If you don't turn these into concentrations, you will get the wrong number. So we need to do that, and therefore you need to find the volume, and it tells you in the question, you've just got to look for it, that the volume is 20.0 dm cubed. So we just have to divide each of these numbers by 20, because that's what the volume is. So we divide by 20.0, and we get 0.1075 for the SO2, and we get 0.0725 for the hydrogen, 0.0175 for the H2S, and 0.0350 for the H2O. So now we've got the numbers we need, and we can put them into the Kc expression. So remember, we had that Kc is equal to H2S times H2O squared divided by SO2 times H2 cubed. So we just put those numbers in there and write this down as an expression. Don't just feed them straight into your calculator, because everybody, including you, needs to see that you've put the right numbers in the right place. So we've got 0.0175 times 0.0350, but it's H2 squared, so that number is going to have to be squared, divided by 0.1075 times 0.0725, and that one is going to have to be cubed, as you can see. If you work that number out, your calculator should tell you that that equals 0.52330 something or other. But you've got to be careful, because it says in the question that it has to be rounded to an appropriate number of significant figures. So what you have to do is to look at the data you've fed in so that you can decide what an appropriate number is. So these two numbers, although I've just written 2.50, were actually given as 2.500, so they were given to 4 significant figures. But this one, 0.350, that was only given to 3, and the volume also was only given to 3. So that's what's limiting our precision, is the 3 significant figure numbers. It doesn't matter that these are more accurate, we're going to be restricted to 3. So we're going to have to restrict our answer to 3. So we just look at that. Remember, that's the first significant figure, so it's going to cut off there. We check that this number isn't big enough to make it round up, but it's not, so that's just equal to 0.523 to 3 significant figures. And then we've got to find the unit. So again, it's well worth your while learning the recipe for the units of K. So let's just write that down, units of Kc. If we define Y as the powers on the top minus the powers on the bottom in your Kc expression, then it's very easy, because the units of K will just be moles to the power Y dm to the minus 3 times Y. So in our case, we can see on the top we've got 2 plus 1 makes 3, and on the bottom we've got 3 plus 1 makes 4. So we've got 3 minus 4, Y is minus 1, and so it's moles to the minus 1, and dm is minus 3 times minus 1, which is plus 3. So it's moles to the minus 1 dm cubed. And that's the answer. Part C asks us, what happens if extra steam gets injected into the volcanic gas? In other words, if the concentration of H2O changes. And it asks us to explain what happens specifically on the relative amount of H2S and SO2, and it asks us to explain it in terms of Kc. Now when it says in terms of Kc, that means you can't use Le Chatelier's principle. Okay? You obviously could work it out that way, and that would be quicker and easier, but when it uses that language in terms of Kc, it means they will ignore anything you say using Le Chatelier's principle. So, the first thing you look at if you're going to have to use Kc is, does the temperature change? Because if it does, Kc changes. If it doesn't, Kc stays the same. And in this case it says specifically that we're to assume that the temperature and pressure are unaltered overall by the injection of the steam. So the first thing we can say is that Kc is unchanged because the temperature is the same. And you should say that, because any argument based on Kc is going to depend on that being the case. So Kc is unchanged because the temperature is unchanged. So say that first, so that it's clear that that's the starting point for your argument. And then you look at what's going to happen to the top line and the bottom line as a result of the change you've made. And in this case it's very simple, because all we're doing is adding in extra steam. So this concentration is going to rise and the other ones are not going to change. Obviously it's a bit hard to see how that would happen in practice, but that's what it's told us to assume. Okay, so we're just saying the concentration of this rises. So therefore the top line is going to get bigger relative to the bottom line because we've increased that term, and therefore the value of the expression is going to get bigger. So that's what we say. Okay, so higher H2O concentration means the top line gets bigger relative to the bottom, which means that the expression value gets bigger. Not Kc, remember Kc has not changed. We've already written that down, so you mustn't say Kc gets bigger. You say the expression value increases and no longer equals Kc. Okay, so we have increased specifically that term. That's made the top line bigger relative to the bottom line, so when you do the division, the answer comes out to be bigger. To get back to equilibrium, we've got to return that expression value to equal Kc again, and obviously that means we've got to make the top line smaller again. So we say that next, that to return to Kc, to return to equilibrium, the value must return to Kc, and we know how to do that because we know it's got to get smaller, which means top line must get smaller and the bottom line bigger, because that will have the effect of making the value smaller again and getting back to Kc. So the top line must get smaller and the bottom line bigger. And how do you make the top line smaller? Well, the equilibrium will shift in the backward direction. Okay, which means that it will shift in the backward direction, or to the left if you like. If you tend to get left and right mixed up, as I do, it's safer to just say shift in the backward direction or the forward direction, but in this case in the backward direction. But you can't stop there, because the question said what happens to the ratio of H2S concentration divided by SO2? Well, you can see that we're going to have less H2S and more SO2. So if we just do this bit over here, we can see that H2S divided by SO2, that's the value it's asked us to comment on, and we can see that that's going to get smaller. When we shift in the backward direction, we use that up, and that's going to get bigger. And therefore you can see that the value of that is going to become a smaller number. So the ratio gets smaller. And you need to say that, or you need at very least to say the H2S gets smaller and the SO2 gets bigger. You might get away with just saying that, but it did actually ask you about that ratio, so you should really comment on that number itself and say that gets smaller. And that's the answer. Now those questions like that based on using Kc to explain the shift in equilibrium, they're not trivial. If you haven't done one before, they're going to be very difficult to work out, but you've done several now. If you haven't got the hang of them yet, don't give up. Just keep coming back, see how the logic flows through them, and eventually you'll get there, and then that's a good job because they're always going to carry several marks, so that's well worth doing.